Okay, so as I mentioned in the final sentence, usually the intensive properties can be computed from the ratio between the two extensive properties. So here we define the extensive property use the capital B, and the extensive property we use the small b in here. So we take we define the one ratio, the extensive b, right, and divided the mass, and as we know the mass also the extensive property, right? So as I mentioned, the two extensive property ratios will equal to the intensive property, small b. So that indicates if your capital B is equal to the mass, then the B will equal to 1, right? So we just define the relationship between the extensive and the intensive properties. Okay, so based on this idea, as we also know that we define, we have the one control volumes, and how many extensive properties inside the control volumes. We use the BCV. That indicates the amount of the extensive property B inside in control volumes. So we use the BC and BCV. Okay, and usually that will can be right by the, maybe we have the B in here, okay, the small b in here, and we have the dm because a piece of the mass, So as you can see, if the capital B is the mass, and then the B is 1, so you can see that will equal to the mCV, and in here the small b is 1, so the integrals along the CV volumes will equal to dm, right? Will equal to the dm. And the later we know that a piece of the dm will equal to the low dv, right? The density multiply the small volume changes. Okay, so the more general formula, we will show that the BCV will integrate along the CV volumes, and the B, we didn't know the B first, and the dm will equal to the CV and the below dv. Okay, so that's the first one. We need to know how many extensive properties inside the CV. CV is our control volumes. Okay, why I would like to introduce the loss of the parameter, because later we would like to discuss the property exchange along the boundary. Okay, so we need to define how property we are looking for. Okay, so we have the BCV. So another is we only discuss the how many property inside the CV volume. But the previous slide, we didn't discuss the how exchanges along the boundary. As we see, introduce the previous slide, we know that the boundary in here, we call that the control surface. And usually we use the CS, the control surface. So in the example showing here, we have the left-hand side is our inflow, and the right-hand side is our outflow. So how physical changes inside? So right now we are looking for the mass. The mass exchange along the boundary. So how can you compute the mass? Like the mass 1, we have the mass 1, and we can see that is the A1 cross-section area multiply the V1, right? A1 multiply V1 is Q1, is discharge. And the discharge multiply the density will equal to the mass flow rate. So the mass flow rate 2, cross-section area 2, also equal to a rho A2 V2, right? So and then there I conclude that the one names is a net mass outflow rate, the net outflow rate. So I use the outflow minus the inflow, the outflow minus the inflow rate. So you can rewrite the equation is rho 2 A2 V2 minus rho 1 A1 V1. And then in here we not assume the density is constant. So we also use the rho 1 and the rho 2. We didn't assume the flow is incompressible flow. So maybe the density can be changed on different space location. Okay? So and another concept, if we based on the dot, we based on the dot per dot. So if we based on the dot per dot idea, as you can compare for the cross-section 1 in here, and we can multiply the A1 factor dot per dot the V1 factors. As you can see, the direction is opposite direction, right? It's the opposite directions. So after the product result in here will be the minus, right? That will the minus. And in the right hand side, you can see that the A2 vectors multiply the V2 velocities. That they are the same directions. So the product result in here will positive. So if you based on the dot product, you can see the final result also is the mass flow 2 minus the mass flow 1. Because the dot product already provided the direction. The right hand side is positive, left hand side is minus. So more general formula you can rewrite. You can rewrite the density is constant, but we have the velocity factors multiply the cross-section area factors plus the density 1 and the V1 factor multiply the A1 cross-section area factors. And normally the result we will have the minus here because the directions of a normal factor is opposite with the flow directions in the inflow cross-section area in here. There the direction is the difference, the right hand side and the left hand side. So that we will the dot product result with the negative. Okay, and actually you may have the many control surface. You may have the many control surface. So you should the sum all of the control surface for the mass flow rate. You need to sum of the all mass flow rate under different control surface. Okay, so this is what we say. So the final we can summarize the previous along the control surface. We can rewrite to be we call that the B, and this is the net. That's the extensive net. Okay, extensive net. And what is extensive net is equal to the sum of the control surface for the mass flow rate. But right now, because the previous slide we call that the net is for the mass flow rate net. So we can write the control surface is equal to a rho V factors dot product with the cross-section area. But right now we change the mass to the extensive. So we rewrite the mass to be the extensive. So right hand side will to be the control surface also, but we have the additional intensive B, the multiply rho V factor multiply the A dot product with the A cross-section areas. Then we can rewrite the summations in here to be the integration with along the control surface, and we have the B rho V and the dot product with the cross-section area factors. But right now we can change because this is integration, so it is a small cross-section area. Okay, so what is the difference? The previous slide we also introduced the BCV. The BCV is equal to, we just integrate along the control volume, right? But we only discuss the B, and we have a low density multiply the D volume, right? Multiply the D volumes. So for the extensive matter property inside the control volume, there is no dot product. But for the property exchange along the boundary right now is control surface, we have the dot product. Okay, so both two parameters are important in the following slide. We need to know that there is the rate, the extensive net along the control surface. Okay, and this is the extensive property inside the control volume. Okay, BCV and the B net. Okay, so right now we have some background idea knowledge, so we can introduce what is the Nanotransport Theory. What is the Nanotransport Theory? Okay, so this is the time point at the t and the several times later delta t. So we have, and we discuss with this is the right now inside is the BCV t, and here is the BCV t multiply the plus the delta t, and the dashed line showing here is our control volume boundary. So the dashed line in here is the control surface. So you can see there highlight it is the control surface. Okay, and outside control surface there are the delta B inside, and at the time point or at the t plus the delta t, there is a delta B outside in that region, and so how can we calculate the extensive property changes in the closed systems? So the next slide we just discuss with the closed systems is all of the systems, and at the time point when the time is equal to t, and in the closed systems with the extensive properties will equal to the BCV plus the delta B in, right? Because this is the region in here and the region inside the control volumes. Okay, and so in the same ideas that we discuss with the also closed systems, but the time change to the t plus delta t. So in that time point, we also discuss the BCV inside, and we have the delta B out in here. So you can see the formula showing here. So we would like to discuss the closed systems, the extensive property in closed system change with the time. So we just delta t over B closed systems at the t plus delta t minus the B closed system t. Okay, so you just put the all of the parameter inside these equations. You can expand the equation to be this formula. Okay, so in the ideas we just combine all of the parameter related to the CV together. So you see here we just combine all of the parameter related to the CV. So we have this item this item is related to the CV. And the outside is the B out, the B out. And this is the B in. This is the B in. Okay? So, and you can see, we can say that this is BCV and DT, right? DBCV DT for this item. And this item, we can say that is equal to the B net. Is equal to the B net. The B net rate. Okay? So I just highlight some, we have know the parameter, the BCV. What is the BCV? The BCV, we do the integrations. We know that along the control volume inside and the B low and the small volume changes, right? So we can compute the BCV change with the time is equal to the DT. We do the integration along the control volume and the B low, D small volumes, okay? And then what is the B rate? The B rate net. We know that it is equal to, we integrate along the control surface. But we have a low, B low V vectors dot with the cross-section area vectors. Okay? So we can put all of the parameters shown here and the B rate go back to our equation showing here. So we can summarize the total extensive property inside the closed systems change with the time will equal to the matters change in the control volumes plus the matters exchange along the control surface boundary. Okay, so we can this is we call that the function showing here is the Nano's. It is a Nanotransport Theory. Okay, this is a Nanotransport Theory. So again, the left hand side is related to the closed system. The change, extensive property change in closed systems will equal to the property change in the control volumes with the time and the property exchange along the control surface. Okay, so the difference. So the slide just summarized. So the left hand side is a Lagrange idea in the closed systems. We discussed the closed systems, the physical property exchange in the closed systems. And right hand side is Euler's concept because we focus on the control volumes, the spatial locations, and we only focus on the control surface exchange along the boundary. Okay, so that's the summarize is very important. This is very important for these chapters, the Nano's transport theory. Okay, so we have some exercise. We discuss how can we apply the Nano's transport theory. So in this, we have two exercises in here. So in this exercise, you can see we have the some flow. This is our inflow, right? And we have the outflow, but the outflow is due to the evaporations. Okay, the outflow is indicate to the evaporations. So we can see we have the outflow in here. So what's the problem? I would like to answer the problem. Answer in here is how about the concentrations after the 1 hour? How about the concentrations in the river after the 1 hour? So you can see maybe this is just for these questions, maybe our control surface is along the water surface and there's the boundary, right? So the blue line showing here is our control surface. And then along the control surface, we have the inflow and another we have the outflow and nothing. So we would like to discuss how concentration changes in the river. How concentration changes in the river after the 1 hour. So we need to know, we need to recalculate the concentrations after the 1 hours. So what is the concentration? The concentration, the unit is the mass. We have the mass. And the bottom, we need to have the volume. So that, and we define this is our concentration. This is our concentration. So you can see we have the original concentration in here is the C0 showing here. This is our initial concentrations. And this is the surface area, the surface area for the water. And this is the water volumes. This is the water volumes. And we have the discharge for the inflow. And we have this concentration for the inflow. Okay, so based on we know that the 1 liter will equal to the 3 minus 3 power cubic meter, right? And we know that the C concentrations, maybe CIN, the concentration for the inflow is the 10 micro mg divided L, and will equal to the 10 mg divided the 10 minus 3 power meter cubic, right? And we know that the mg also equal to the 10 minus 3 power. So the concentration in here, the unit will to be the 10 grams per meter cubic, right? The G divided the meters cubic. Okay, so we would like to recalculate the final concentration after the 1 hour. So the 1 hour, we know that the 1 hour is equal to the 3600 second. Okay, 3600 second. So we first calculate the initial mass we have. The initial mass we have. So how can we calculate? Because we already know the C0, right? And the C0 multiply the total volumes will equal to the initial mass. And we have the total volume is total initial concentration is 0.5, and G divided the meter cubic, right? G divided the cube in here, and multiply the total volume is the 500 meter cubic. Okay, so you can use your calculator to calculate the initial volumes. Initial mass is equal to a 250 G. And what's the input mass? The input mass, we have the inflow concentrations, CIN, and we know that we have the Q in here. So the CIN multiply the QIN and multiply the delta T. So we know that the delta T is the 1 hour later. The 1 hour later, and it will equal to what's the number you can put inside we have the 10 concentrations, the G divided the cubic meter, and the discharge is 0.02 meter cubic per second, right? And then we need to multiply additional delta T is 3600 seconds. And then you can use the calculator to compute the weight, the mass contributed by inflow. So the 10 multiply the 0.02 and then multiply the time is equal to the 720 G. And what is the outflow? The outflow mass is caused by the evaporations. So the evaporation defined here is related to the different area will control different evaporation speed. Okay, so we just have the we know that this is evaporation rate is 0.42, and the unit is mg divided the m squared divided the second, right? And we know that the total area in here of the water surface, so we have the 400 meters water surface, okay? And divided the time delta t is 3600 seconds. And notice that here the dimensional is the ng. So for your answer, final answer, you need to convert it to the g. So you can calculate the answer by your calculator, and I double check by myself. So that will equal to the 604.8 g. Okay, so we have the final mass on the upper items. So how delta V changed? So most significant changes for the volume is caused by the inflow, right? Because all the Q in spill out in the tank, right? So we know that we have the Q in, and multiply the delta T is the total volume changes caused by the inflow. And we have the secondary volume changes will caused by the evaporation. But the evaporation, the contribute in the volume change is quite smaller compared to the inflow. So in here we neglect the volume change caused by the evaporation. So we just directly calculate the delta V changes caused by the inflow. So the Q in is the 0.02 meter cubic per second, and then multiply the 3600 seconds, and you can use your calculator to check the answer. So the answer is equal to the 72 meter cubic. So we can go back to calculate the final concentrations will equal to the initial mass is 250 G plus the inflow in here is 720 G, and the outflow in here, so we need to minus because it is the outflow. Okay, and the original volume in here is the 5 meter cubic plus the additional volume changes is 72 meter cubic. So we can calculate the final answers. So I check by myself. So the answer is equal to 0.638, and the dimensional is the G divided the meter cubic. And you can also say that is around the 0.64 and the mg divided the liter. Okay, so the conditions is showing here is the dangerous because the 1 hour later the concentration in the water is increased. So that means maybe some industry outside the channel, but they spill out some methods and will let the river concentration increase 1 hour later. So that's very dangerous if they just spill out maybe 1 day, and the concentration in the river will increase a lot, will cause some people health problem, right? Okay, so this is the increase is so that's very dangerous. But I just point out this exercise. You just need need to define where is your control service. And inside the control service, we call that the control volumes. So right now the control volume is our river channel. And you can discuss some property changes in the control volumes. For this example, we just discuss with the concentration. Okay, so the second exercise. So again, we just write down the nanos. So this is the equation for our Nanotransport theory, right? So we have the closed system left hand side, and the control volume and the control service integrations. Okay, so this is what the change rate of the contaminations in the rivers. Okay, so again we need to define our control service. So the dashed line is our control service, and again we have the inflow left hand side. So left hand side is our inflow, and the right hand side is our outflow. And we have the discharge and the concentration again. So for this problem, I also highlight the material inside the river will have the self-decay. So this is the self-decay that tells us the dt in that case is equal to, because right now our discuss the extensive properties is the mass. So that's the dm dt in the closed systems will equal to the minus 0.06 g per second. Okay, because the closed systems, so we cannot exchange, right? So we call that if some difference will caused by a self-decay. Because in the closed system, we cannot exchange any properties along the boundary. So if you see some difference in physical property, that we call that the self-decay. OK， 在封闭的系统里面，我们是不可能可以有物质的转换嘛。所以如果在封闭的系统里面有东西，物质上面不管是增加还是减少，那在我们的案例，这个叫做它自己减少了，所以我们就说它自己有一个 self 的 decay， 自身的衰减。Okay, so we know that we can rewrite the Nano's transport equation. So in here is dm dt in closed systems will equal to the dt and the mass in the control volumes, and plus the mass flow rate out minus the mass flow rate in. Okay, the mass flow rate out and the mass flow rate in. As I mentioned, we already know this is item equal to the minus 0.06 g per second. So how about the mass flow out? We have the Q out in here and the C out in here, right? So we know that this will equal to the Q out multiply the concentration C out. And the number will equal to the 10 meter cubic per second multiply the 0.05 G per meter cubic, right? So that will equal to the 0.5 G per second. This is caused by the mass outflow. And what is the inflow? The inflow, we have the Q in and the CIN in here. So again, we have the QIN multiplied the CIN will equal to the QIN is 0.03 meter cubic per second multiply the CIN is 20 G per cubic meter. Okay, So you can see that the answer is equal to 0.6 G per second. So our problem, we need to tell the answer is, the question is dmCV dt, how large it is. That's the mass changes rate in the control volume. The control volume right now is the channel, river channel. Okay, so we can reorganize the equation. We know that the dmCV dt, the mass in the control volume change rate, will equal to a dm dt in the cross distance minus the m rate plus the n rate in. Okay, so we just put all of the number inside in the equations, and minus the 0.6 G per second plus the 0.6 G per second. So finally we know that the answer will equal to 0.04 G per second. So this is our final answers. Okay, so again, the question's most important thing, you need to identify which items you already know and what are the unknown parameters. So for this exercise, the unknown parameter is the change rate, the mass change rate in the river channel. The river channel right now is our control volume systems. This is the red regions, red color regions is our control volume. And the yellow line is our control service. So this is CV and the yellow line is our CS. Okay? So I think the most difficult is how can you determine the control service and the control volume. So it depends on your questions. Okay? So in the following, I will spend 5 minutes to very quickly introduce what is the continuity equations. What is the continuity equation? So as you can see, the continuity equation have a very important assumption. We assume the mass is always conservation. Okay, the mass is always have the balance and always the conservation. So that indicates the mass didn't change in the closed systems. The mass didn't change in the closed systems. So that's a mass conservation. So if the assumption is correct, so the item in here, we don't have the mass change in the closed system, right? So we don't have this item. Okay? And now here we already know, because we discussed the B is the mass, so the small b is equal to 1. So the nanotransport theory tells us that dm dt will equal to the m change in the CV and the m exchange along the control service. So because we don't have this item, so we can rewrite the equation only have the control volume and the control service. Okay, so and this is the equation, we call that the continuity equation, right? 连续方程，这个很重要哦。当我们假设系统里面的质量，封闭系统里面的质量是完全满足质量守恒的，所以没有任何东西消失，就不会随着时间有变化。所以雷诺传输方程的左边 closed system 这个项次就会归零。那它归零了以后，剩下来的东西我们就叫做连续方程。Okay, so that's only one assumption is the mass is conservation. The mass is conservation. So we remove the items for the closed systems. The physical property changes in the closed systems. So we don't have this item. Okay, so that's the idea. We only have the So we can rewrite the equation because we have because we don't have the consistent, so the dmCV dt plus the n out minus the n in will equal to 0, right? So we reorganize the equation, the mCV change with the time will equal to the n in minus the n out. So if this item is the positive, that indicates the inflow support is larger than the outflow, right? So we call that, in that case, we call that the accumulations, because the physical property will accumulate in the control volumes. Okay, so that we just symbolize the nanotransport function to be the continuity equations. Okay, so that's the working equations. So I just emphasize the step 2, because usually it is very difficult to depict where is your control service for the questions. So we have the one exercise. I would like to use this is our final exercise today. How can we depict the control service? And the inside the control service, we call that our control volume. Okay? So what's the problem? For this problem, we know that we have the inflow in here, and we have the outflow in here. And what we already know, we know that the speed of the incoming, so we have the V1. The V1 is incoming velocity is 7 meters per second. And with the cross-section area in here, the cross-section area, the A1 is equal to 0.0025 meter square. And our liquid is the water, and also flow out with the discharge. So the Q2, the flow out with the discharge is equal to 0.003 meter cubic per second. And we know that the water density is the 1,000 kilograms per cubic meter. So what's the problem? What the rate is which the water is being stored or removed from the tank? So the problem would like to you to answer the water surface is increased or downward. So you need to determine by yourself. So as you can see the example, we depict the control surface like the dashed line showing here. And we can exchange, right? So we have the inflow. We can exchange the property along the surface, right? So we have the inflow and we have the one outflow in here. Okay? And then we don't have the because this is a closed system. So there's no any the mass flow out. We closed system, any didn't change in the mass. So for our equation, we just based on the continuity equation. We have a dmCV dt plus the n out, right? Minus the n in, and will equal to 0. This is the continuity equations. Okay, so the problem is the item in here is the positive or negative. If this the mCV dt is positive, that indicates the water surface increase, right? Because the volume in the control, the mass in the control volume is increased. Okay, so we need to answer is positive or not. So we know that the mCV dt is equal to the n rate I minus the n rate out. So what is n rate I? So we have the density is the water, and we have the V1 velocity multiplied A1. V1 multiplied A1 is discharge. Discharge multiplied density is equal to the mass flow rate. Okay, and then minus the n out. N out is equal to the low Q2. The low Q2. So that will equal to, we take the density outside. So inside we have a V1A1 minus the Q2. So we put the number inside, we have a density 1000 kilograms per meter cubic. Multiply the V1 is the 7 meter per second. Multiply the A1 is 0.0025 meters square. Okay, and that will minus the Q2 is the 0.003 meter cubic per second. Okay, so you can calculate the final answer by yourself, and I double check the number is correct or not. So it will equal to the 14.5 kilogram per second. So it is a positive. So we can conclude that the water will be stored, right? Because the water surface will increase. Okay, but one thing is very important I would like to highlight. Because the water level increase, okay? But originally, here is the air, right? So when the water increase, that means the air will spill out. So, but as we know, the air, the density may be equal to the 1.2 kilogram per meter cubic. It's quite smaller compared to the water density. So we just neglect the volume change caused by the air. Because the air density is quite smaller compared to the water. So as the sentence showing here, so we just neglect effects caused by the air spill out. Okay, so this is just a simple exercise. If you depict the control surface and you based on the continuity equation, you can calculate the mass changed in the tank, the water tank. OK， 这个非常重要，就是因为我觉得最难的是，如果我不画 control surface 给你的话，你要自己决定你的 control surface 在哪。你要自己决定你的 control surface 在哪。那怎么决定？这个 surface 就一定会有进跟出嘛。所以我会去决定有进出的地方就是我的 control surface， 因为只有在 control surface 上才可以做交换嘛。所以我就会看我的问题哪里是 inflow， 哪里是 outflow， 那它就一定是我的边界。OK， 那会不会因为你画的边界不一样，那答案就不一样？当然不会啊，因为你的 in 还是有 in 嘛， out 还是有 out， 所以不同的决定 control surface 的方式会影响你的解答的方法，可是最后的答案会是一样的。OK， 那我下次上课会再提醒各位这个地方。好。